You may have noticed that some fruits may seem to almost ripen overnight, while others can sit in your refrigerator for weeks and you might barely notice anything different. For example, you can buy a banana when it's green and fresh in the stores. However, when you take it home and leave it on the counter for just a few days, the banana turns yellow and sometimes spotty and a lot more ripe. But then you have fruits like oranges and blueberries where you can leave them for a while without them really changing their characteristics at all. So, why does this happen? Well, it turns out that there are two categories of fruits when it comes to this. The first category is climacteric fruits, and the other is non climacteric fruits. Climacteric fruits like apples, peaches, and bananas go through a major increase in respiration and ethylene production as they ripen. Non-climacteric fruits like oranges and berries don't follow the same pattern when they ripen. And this brings us to something called ethylene. Ethylene is a natural plant hormone that plays a very important role in triggering the ripening rates of climacteric fruits. When ethylene interacts with receptors in the fruit, it basically causes a chain of reactions that prompts the ripening to happen. The fruit becomes softer, changes color, develops its flavor and aroma, and eventually becomes more mature. And normally, that's exactly what we want. We want our fruit to ripen. But the problem is, fruit doesn't just go from a farm to a grocery store immediately. It might have to be stored or transported or distributed for an extended period of time, depending on where the fruit is being produced and where its final destination is. And during that process, if the fruit ripens too fast, then before the fruit can even reach the consumer, the fruit may already have lost a lot of its original firmness and quality to it. And that's where 1-MCP, or 1-methylcyclopropene, comes in. 1-MCP is one of the most widely used methods to delay fruit ripening. So how exactly does it work? Essentially, 1-MCP can bind to the same ethylene receptors that ethylene itself binds to. When 1-MCP occupies these receptors, it prevents ethylene from activating the processes that is associated with ripening. So essentially the role 1-MCP is to block the ethylene receptors temporarily before ethylene gets the chance to activate it. The important thing is that 1-MCP doesn't necessarily stop the fruit from producing ethylene. Instead, it interferes with the fruit's ability to respond to it. And because of that, processes like color changes and the fruit softening can be delayed, which allows for the fruit to maintain its quality for longer. However, there's a limitation to this. The effect of 1-MCP is only temporary because over time, fruits can develop more ethylene receptors. Even if you treat the fruit once with 1-MCP, eventually more ethylene receptors will develop and the ethylene can interact with those new receptors, which then triggers further ripening. This becomes especially important when talking about long-term storage or transportation. The conventional 1-MCP treatment is often a instant release delivery system, where a relatively large amount of 1-MCP is released during a single rapid treatment period. Now, an instant release delivery system can work really well for an initial treatment, but if the effect is temporary, then you start to wonder, what if we could keep 1-MCP releasing for a longer period of time? That's basically where controlled release delivery systems come in. Instead of releasing most of the 1-MCP all at once, a controlled release delivery system is designed to release the 1-MCP over a longer and controlled period of time. As for these controlled release delivery systems, there isn't just one way to design a system like this. You can change the material that carries the 1-MCP, you can change the surrounding environment of the fruits, you can manipulate the relative humidity, you can change the formula used to make the 1-MCP coatings. And all of these things potentially affect how quickly 1-MCP is released over that controlled period of time. So now the question becomes, how quickly should 1-MCP be released? How long should the controlled release delivery system last? And what materials would be used to do the testing? And how does manipulating the relative humidity or the surrounding environment affect the rate of the release? Those are some of the questions I started looking at during my internship at a food packaging and food science lab at Rutgers University. My research largely focused on using a 1-MCP shellac coating and applying that coating to various different compostable packaging materials while also manipulating the relative humidity to measure its potential for being a controlled release delivery system for 1-MCP. And beyond just measuring the release kinetics itself, there's another question. Does that release rate actually make a difference in the fruit compared to an instant release delivery system? That's why the bioefficacy and the biological responses of the climactic fruits are so important when testing. Because ultimately, having a really interesting release curve doesn't really mean anything if it doesn't slow down fruit ripening. One of the biggest things I learned throughout my 2-month internship at the lab was how there are so many different ways you could potentially approach a problem. Before I started my experiment in the lab and researching a bit more about this field, I would have thought that fruit preservation seemed pretty simple. If fruit is ripening too fast, then just find something that will slow it down. But once you actually start researching it, you find that there are so many variables involved in the process. You can change the delivery method, the packaging material, the relative humidity, and on top of that, you have to find out how the fruit actually responds. So at the end of the day, research isn't necessarily about finding one perfect solution right away. A lot of the times, it's about taking a problem that already exists, understanding the mechanisms behind that problem, and the variables involved in it, and trying to optimize them in order to find a solution. People already know that 1-MCP can delay fruit ripening. The question is how we can make that process more effective, more practical, and potentially increase its accessibility. And on top of that, there's an even bigger reason on why this matters. If we can keep fruit fresh for longer and increase the amount of time it stays in its original quality, then we may also be able to reduce the amount of food that gets thrown away or lost during the storage or transportation process. When you think about all those resources that go into producing and storing and transporting the fruit, reducing food waste could have environmental benefits as well. So, something as simple as a banana becoming soft or an apple changing color is actually part of a much larger process, a much larger system that involves plant biology and the chemistry behind it, material science, packaging, and even environmental sustainability. And that is probably what I took away the most from this research. Sometimes solving a problem isn't about finding a completely new idea to tackle that problem. It's about understanding the smaller mechanisms behind the problem, figuring out which variables actually matter, and then finding a way to put all those pieces together to make the solution better.